What is velocity? Have you ever noticed while you're driving, there is a device called speedometer that is measuring a numerical quantity that is followed by kilometers per hour or miles per hour? Have you ever given a thought of what does this mean? Well, this means that this device measures the change in distance to a given function of time. And, as innocent as this may seem, this contains pretty cool mathematics. And in mathematics, these changes are denoted by something like the x of a dt, and this is what mathematicians call a derivative. This derivative is only defined locally. This means it can only provide information of a given point in time and space. To better understand what we were talking about, let's go for a drive in your car. The position of the car can and will be represented by a set which contains information of the entire trajectory as well as the distance traveled, along with all the points where you were in the past, are in the present, or will be in the future. You can make pairs of the time and position of your trajectory. This pairing can be represented by a mapping from the time axis to the position axis, and this will be known as your position function. We've said that to measure velocity, we need something like the x of a dt. So if we use the position function and choose a dt of 30 minutes, and by knowing the x, we can finally know the velocity. Here we're going to have two velocity readings. One is going to be for each time interval. Now let's shrink dt to 20 minutes. So we end up with 3 velocities. And here we see that the smaller the interval gets, the better the tangent lines approximate the function. So if we keep shrinking dt now to 10 minutes, we'll get an even better fit. Look that here we keep the dt's constant while the dx's were different. This is simply due to change in velocity, implying that we're going to have different velocities for each interval. For this part, let's study some funky paths. And here we take these paths as our new position functions. So let's take a couple of steps back. And we're going to keep our eyes on one point. And for this example, this point is going to be really special, because every path is going to have this point in common. We already know that every path is going to have its own velocity at that given point. This velocity basically contains information of what's the next move for every path, kind of like a fraction of its destiny. This arrow of destiny is what physicists call a vector. And because all vectors will lie tangentially to the position function, the space where vectors live is called a tangent space. And this will be our first example of a linear space. So, what's a linear space? Well, a linear space is a mathematical structure in which its elements are called vectors, and it basically contains two operations: scaling the vectors and summing the vectors. In future videos, we will see that any tangent space is a vector space that will encode all the local properties of a function or a space. At the latter, let's take a sphere. And if we look really close to the surface, we could almost say that it's flat. Such is the case that you see the floor where you're standing completely flat, despite the fact that you live in a spherical shape like planet. Well, at least that's what they say. With this, we'll stretch our observations to say that every object moving on the surface of the Earth, its velocity is going to be contained in its own tangent space. If we're going to study the movement of an object in greater detail, we'll eventually need to describe its acceleration, but unfortunately this requires a much more complicated object called a connection. This connection will allow us to transport information from one tangent space to another, and this was a key element Einstein used to describe gravity in his famous theory of General Relativity, and this and more will be explained in future videos. Thanks for watching. So, if you like this video and want more animations to come, hit the like button and subscribe.